right, thank you. Okay, so we want to look at qualitative organic chemistry. And some people call this wet chemistry, because we'll be using a bunch of reagents to try to identify the presence or absence of certain functional groups in organic compounds. So there are, when we do analyses of compounds, there are two approaches we can take. One is, so analyses can really fall into two very broad categories. There are quantitative, and then there are qualitative. And quantitative analyses speak to how much of a substance is present, right? So is it 10 ppm, or is it what's a part per billion, or the mass percentage, or the molality, or the molarity, and so on. So that's a quantitative aspect. And we do some of that in organic chemistry, but we're much more concerned in qualitation, which is what is present. And so we could be asking is, how much what do we have benzene, do we have acetone, and so on. But for this part of the course, what we're really more interested in is the presence or absence of functional groups, right? So we're looking for the presence or absence of functional groups or of certain substructures. So over this part of the course, we'll be looking to see whether a compound contains a carbonyl, whether it contains a haloalkane, and if it does, is the haloalkane a chloro-bromo-iodo? Does it have a methyl carbonyl or a methyl carbonol, and that sort of stuff. And further, for organic chemistry, we can divide the qualitative analysis into two major areas, and this is a bit of a stretch, but two major areas. One is wet chemistry, and the other is spectroscopy. Right? Spectroscopy or spectrometry, because there's a slight difference between the two. So what we will do in this lecture is look at the wet chemical tests, right? And later on we will delve into spectroscopy. For us in spectroscopy, we're looking at 4 different areas. We'll be looking at IR, at UV-Vis, at NMR, and then at what basically is mass spec, right? And mass and NMR is both proton NMR, and we look a little bit at carbon-13 NMR. So this is a preview of what's to come. So we spent today's lecture on wet chemistry, and then over the course of really a week and a half, maybe 2 weeks, we'll be looking at spectroscopy, sort of nuanced into those various subsections. So let's get into wet chemistry, and what this will basically look like is something you may have seen in Gen Chem, maybe even in high school chemistry. We will subdivide this into experiment, then an observation, and then inference, and then we'll say the chemistry. So what are we doing? What will we observe? What our conclusion will be based upon an observation, and then to get a sense of what are the chemical principles behind the experiment. And in this far column, I'll say a class or functional group. Okay, so we don't do reactions on alkanes, right? I should phrase that. There are no wet chemical tests for alkanes. And the reason is alkanes only undergo, as far as we're concerned, two reactions. They burn, and they also react with halogen and light. But that reaction is very, very slow, and that's not something that we actually will do as a wet chemical test. In fact, the way you would probably identify an alkane through wet chemistry is that it's a compound that gives none of the other reactions. And if it gives none of the other reactions, that compound is going to be an alkane. So before we get into the table of the different tests, I will point out that typically what happens is the organic chemist will observe the sample and do what we call preliminary tests. So before we get into this, let me just talk a little bit about preliminary tests. And preliminary tests are usually just visual tests. And they involve observing the compound, getting a smell of the compound, and then there's some solubility ones that we will look at in some more detail. So what we would say is, so the preliminary tests are visual. So we look to see whether the compound is a solid, liquid, or gas. If it's solid, if it's crystalline, or amorphous. We also look at its color. Then we do odor tests, and we see if it is fruity or floral. Then we see if it is pungent, and we look for a fishy smell. And then we look for a, let's say, steak. And then there's solubility tests that we will look at in some more detail later on. So I'll just say, if your compound is solid, then that would suggest that either so that means that room temperature does not provide enough thermal energy to melt it, which either implies the compound is heavy, right? Or the compound may have strong intermolecular forces. Maybe it is hydrogen bonded, or maybe it might be a little bit heavy and has dipole-dipole bonds. It is rare for compounds that are van der Waals bonded to be solid, unless it's really massive. So things like naphthalene, for example, or candle wax are examples of really heavy compounds that are van der Waals bonded. So if your compound is solid, then either it has hydrogen bonds, or maybe it's got dipole-dipole bonds, but it's relatively heavy. Or maybe it's got van der Waals forces, but then it's really heavy. So things like sugar, sucrose and so on, those are hydrogen bonded, which is why they're solid. Candle wax, naphthalene are very heavy compounds, but they're van der Waals bonded. If it's liquid, then that suggests that 25 degrees Celsius provides enough energy to melt it, but not to boil it. So that says something about the intermolecular forces, right? And the mass. The intermolecular forces may be significant, but not really strong. And the mass is probably somewhat lighter. And a good example of that is water, right? Water is just 18 grams per mole, which is exceedingly small. But water is a liquid because of the very strong hydrogen bonding. So there's the marriage between the nature of the bonds as well as the mass of the compound. Obviously, the compound is a gas at room temperature. That suggests that that the intermolecular forces are very weak, and that the mass of the compound is small. If the substance, when solid, is crystalline, what that says is that there are very strong intermolecular forces. Typically, these are hydrogen bonds. Because a crystalline structure involves order on the molecular level. So if we're seeing order on the macroscopic scale, in other words, crystals, that betrays order at the molecular level. And that kind of order is only possible if we are locking particles in place and holding them there. That's only possible if the intermolecular forces are pretty strong. So crystalline compounds are usually hydrogen bonded. Now these are organic, right? So we know that for inorganics, right? Inorganics are often crystalline because they are ionic bonds, which are also very strong bonds. But for organic compounds, if you are crystalline, there's a 99.99% certainty that the compound is hydrogen bonded. If it's amorphous, powdery, then there's some other sort of intermolecular forces, dipole-dipole, perhaps even van der Waals. Then color. If the compound, most organic compounds are white, which means they're not absorbing light in the visible band. If the compound is colored, what that tells us is that there is extended conjugation. And we'll see that in more detail later on. But for something to be colored, it must be absorbing light. So if it absorbs violet light, it looks red. If it absorbs red light, it looks violet. Okay? Or if it absorbs red-orange light, it looks sort of blue-violet. So the color of a compound is indicative of whether or not it has extended conjugation. And we'll see examples of that in a minute. Or whether it doesn't. So if you're white, no extended conjugation. If you're colored, extended conjugation. And you look at the sample and it takes you 5 seconds to observe it. And then those are the conclusions that come to mind. It takes you another 5 seconds to get a whiff of the compound. We don't just stuff it on our nose, right? We sort of waft the vapors towards ourselves. If it has a fruity or floral smell, and organic chemists distinguish fruity and floral from sweet. But if it has a fruity or floral smell, it's most likely an ester, right? So this would imply it's an ester, right? And so most of the smells of fruits all are based upon the presence of one or more esters that are generated by biological processes. And we can actually, in an organic lab, make strawberry flavor, pineapple, coconut, mango, banana, pear, rum. And it's kind of interesting when you buy, if you go to the store and you buy orange juice, a gallon of orange juice is probably, what, $5 a gallon? But when you buy orange drinks, that's probably about $1, maybe $1.50 a gallon. And the reason is the juice is made from the fruit, right? You take, somebody grows the fruit and harvests the fruit, squeezes the fruit or whatever. That takes a lot of work, right? And so you pay the cost for that. So that's like $5 a gallon. But drinks are synthesized en masse in an organic lab. That's pretty cheap, right? And so that actually is cheaper. And what they'll say is that if you buy things like Sunny D, they'll say made with real orange juice. Well, that's probably true. They probably put 2 or 3 drops of it in a gallon of water. But then they add flavorings, they add colors, organic compounds with colors, right? And they add the ester for orange, right? And they just add sugar. And maybe they'll say it contains vitamin C because they added vitamin C. But those things are mixed up in the lab. And they're actually dirt cheap, which is why you can buy them cheaper. So if you can afford it, buy the juice, not the drink. If it's got a pungent smell, that's most likely an acid. If it's got a fishy smell, it's most likely an amine. So RNH2, or it could be R2NH, or even R3N, right? So some sort of amine. If it's a foul smell, then it's a thiol or mercaptan. So RSH. So these are things you observe immediately, right? So it takes you 10 seconds to look at the state at room temperature, and the color, and to get the smell. And there's certain conclusions we make from that. The solubility test, we'll do those as we move along. Okay, so those are preliminary tests that you would run in the first 20 seconds of your analysis. And they give you a guide, not much more than that. Okay, so we're going to look now at the various classes of organic compounds, different functional groups, and at the common tests to determine their presence. So let's start with alkenes and alkynes. We'll group these together, although there's a little bit of a difference as we see in a second. So with alkenes and alkynes, we could add bromine in water or bromine in carbon tetrachloride. And the observation would be immediate or rapid decolorization. So if I, and these are typically done in well plates, so I will have my organic sample, my unknown, I would put it into one of the well plates, and I'll add a drop of bromine and carbon tet or bromine water. If the purplish brownish color of the bromine is discharged immediately, then that's an indication that I have carbon-carbon unsaturation with an alkene or an alkyne. And so if I see immediate decolorization, I'll say C double bond C or C triple bond C present. And what's happening here in terms of the chemistry, so let me erase this part. What's happening in terms of the chemistry is that we are adding the halogen across the double bond. So in a nutshell, the alkene when I add Br2, I get in carbon tet, I get an anti-addition, and I'm not going to go through the mechanism, but I get an anti-addition of bromine across the double bond. And whereas this thing is colored, whereas bromine in carbon tet is a sort of reddish brownish sort of color, the dibromo compound is colorless. So this is colorless. The alkene is typically colorless, but this is sort of reddish brown. So when you add a reddish brown liquid to the colorless solution, it forms a colorless product, which means this color is discharged. This reaction, if you remember from your organic one, goes via the bromonium ion, and then the bromine attacks on the other side, blah, blah, blah. If instead we have the alkyne, then the reaction is very much the same. We will add across each double bond and end up with the tetrabromo product. So we end up with the tetrabromo product. So Br, Br, H, Br, Br, and H. And again, this is also colorless. So when you add bromine and carbon tet to a compound, to an unknown compound, and there is an immediate decolorization, that implies that the compound contains carbon-carbon unsaturation. Another good test is acidified permanganate. If you add permanganate to an alkene or an alkyne, if you add permanganate to an alkene or an alkyne, and you get, again, immediate decolorization, that also implies that it's an alkene or an alkyne. Now I'm going to put an asterisk here because this reaction goes in the following way. So the alkene, let's say, and you guys remember this again from your organic one, reacts with permanganate. And what you make, so this is purple, right? Permanganate is purple. What this makes is the manganate ester, at least initially. And that breaks up eventually in the presence of your base. So this is basic permanganate. In the presence of base, and that gives rise to the diol. and you do the diol, you make the syn addition of the diol. But what you make is you go from the purple permanganate to the colorless products. And all of this you guys should have covered in Organic 1. So you go from purple permanganate to the colorless product. So that decolorization is indicative of the presence of carbon-carbon saturation. The problem is permanganate also converts things like primary alcohols, secondary alcohols, and aldehydes. It can oxidize those. And in the process, it also becomes decolorized. So whereas the bromine and carbon tet, or the bromine and water, are unique for alkenes and alkynes, the permanganate is not. So if I added permanganate to an unknown substance and it was decolorized, I could say, well, that could be an alkene or an alkyne, but it could also be an aldehyde, a primary alcohol, or a secondary alcohol. So I'd have to do other tests to confirm. But if I add bromine and carbon tet to an unknown and it was decolorized, it was just an alkene or an alkyne. So maybe what I could do is do the permanganate test first, which limits my options, followed by the bromine and carbon tet test. Okay? The other one, this is specific to terminal alkynes. Is if I add either Tollin's reagent or Benedict's solution, Benedict's or Fehling's solution. And these are basically M, the metal diamino 1 cation, where the metal is either silver or copper. So when the metal is silver, this is Tollin's reagent. When the metal is copper, then this is either Benedict's solution or Fehling's solution. The cation is the active part, and it's the same for Benedict's and Fehling's. The anion varies from tartarate or citrate, and it doesn't really matter. If I add Tollin's reagent or Benedict's solution to an unknown compound, and I get a dirty precipitate, which explodes on drying, and that is a wow event. That would imply you're dealing with a terminal alkyne, right? You're dealing with a terminal alkyne, right? So it's a terminal alkyne. And the chemistry here, quite simply, is that the species reacts, and I'll just write it as a Tollin's reagent. It gives rise to what's called the metal acetylide. Maybe I'll just do M. It gives rise to the metal acetylide. This is called the metal, so it can be silver or copper acetylide. Metal acetylides are insoluble in the aqueous solution, and they, as I said, they are shock sensitive. So when you remove the water, as you sort of dry them, when the drying crystals rub against each other, it's shock sensitive. It literally explodes. So this is not something you want to do for fun. It's actually quite dangerous. So imagine then, I'm given an unknown, and I add to it bromine and carbon tet, and it gets decolorized. Okay, so I know this is an alkene or an alkyne. Maybe my second experiment is to take another sample of that compound and add Tollin's reagent. And if I get a dirty precipitate, then my compound, I can eliminate alkenes. It's not an alkene, it's an alkyne, and specifically a terminal alkyne. Right? So in the space of 2 tests, I now have a substructure. My compound is a terminal alkyne. Now maybe I'll add the Tollin's reagent and nothing will happen, so at least I know it's not a terminal alkyne. Either it's an alkene or an internal alkyne. Right? So I can make observations, right, sequential observations, based upon the properties. I'm going to make a point here. Tollens reagent or Benedict solution or Fehling solution, they're used in two contexts. This is one, which you have met in Organic 1, and the other we've met recently in Organic 2, which is that they are used to oxidize aldehydes to carboxylic acids. And when you do the reaction with Tollens reagent, you get a silver mirror. But when you do it with copper, right, Benedict's or Fehling solution, you don't get a copper mirror, you get a dirty reddish brown solid, which you could basically say is a dirty precipitate. So if you do it with Tollens with Benedict solution or Fehling's, and you get a dirty precipitate, that can either mean it's a terminal alkyne, making the acetylate, or it's an aldehyde being oxidized with carboxylic acid. But there are ways of distinguishing aldehydes from terminal alkynes, which you'll see in a minute. Aldehydes will not, for example, decolorize bromine in carbon 10. So if I had done the bromine in carbon 10 first, and then seen the 2D precipitate, it couldn't possibly be an aldehyde. Okay, so I'm going to use the same table, and we're going to go now to rather than the hydrocarbons, the alkenes and alkynes, we're going to look at compounds at the alcohol level. So if I start with some of the haloalkane, so there are specific tests for haloalkanes, and so let's say haloalkane. So I'm going to add to this ethanolic silver nitrate. So I'm going to take silver nitrate in ethanol. The ethanol is used to dissolve the organic compound. And ethanol, it's a polar enough solvent, it's hydrogen bonding, so the silver nitrate will ionize in it. It also serves as a matrix to dissolve the haloalkane. Now, if I get an immediate precipitate, that implies we're dealing with a tertiary or allyl type halide. If I get a slow precipitation, often on warming, that implies it's a secondary haloalkane. And if I get no reaction, either it's a primary or methyl, well, it couldn't be methyl, it's primary haloalkane, or not a haloalkane. Okay, so what's the chemistry here? So it turns out that if I had Rx, it turns out that silver is what's called a halophile. And there are a couple of examples in Organic 2 that we meet, so here's the most prominent. That's called a halophile. In other words, it has an affinity, a love, for halogens. So what happens in this reaction is the haloalkane, by virtue of the lone pair of electrons on the halogen, chlorine, bromine, iodine, will complex or react with the silver plus. This is the base, and that's the acid. So acting as a Lewis base, Lewis acid, and generate this polarized complex. What happens next is that the Rx breaks up to give solid silver halide. That's the precipitate, right? The solid silver halide. And it makes R plus. The R plus then reacts with the ethanol, and this also has some water. So it reacts with the ethanol and water combination. So it reacts with the ethanol and water combination, and basically that gives ROH or ROET. But the rate determining step in this reaction is this one. That is the rate determining step or the rate limiting step. That controls the kinetics. So the faster this carbocation forms, if it forms at all, the faster I see precipitate, because these things happen simultaneously. Carbocation forms at the same time the precipitate forms. So the faster the carbocation forms, the faster the precipitate forms. Well, what makes the carbocation form quickly? And the answer is, the more stable it is. So a stable carbocation forms faster, and a less stable one takes more time to form. So in other words, in a graph, in a reaction profile diagram of enthalpy against reaction coordinate, which has a time parameter in it, if the formation of the carbocation is easy, then it's fast, right? It basically takes this much time. But if formation of the carbocation requires significant input of energy, that takes a longer time. When is the carbocation stable? When it is tertiary, right? So there are multiple R groups feeding electron density into the carbocation, right? So when it's tertiary, it's very stable, so it forms rapidly. This is tertiary, this is secondary. Or when it's allyl type. So if it's allyl or benzylic or so on, these are resonance stabilized, and so they form quickly. If the carbocation is secondary, so if I'm dealing with, a halide of this type, well, secondary carbocations can form, they just are less stable, and therefore they take more time, more energy, and therefore more time to be formed. So that reaction is slower, and you often have to warm it. So the rate at which the precipitation occurs is indicative of the character of the haloalkane. If it forms rapidly, that is going to be a tertiary or allyl halide, because that leads to the stabilized, either inductively stabilized tertiary carbocation, or the resonance stabilized allyl or benzyl carbocation, right? Allyl or benzyl. That's why we call them allyl type, because they look similar, resonance stabilized. If I see a precipitate form after warming, so I'm giving it the energy to climb the barrier, and that's going to take some time, then that's secondary. If I don't see a precipitate, then it means either it's a primary haloalkane, which will not form the carbocation, or it's not a haloalkane at all. But this test has another degree to it, because the silver X, these have different colors. So when X is chlorine, right? So when it's silver chloride, this is a white solid. When it's silver bromide, this is a pale yellow solid. When it's silver iodide, this is a deep, really rich yellow color. So if I have an unknown and I add to it ethanolic silver nitrate, and I see immediate formation of a deep yellow precipitate, well, I know two things. I know it's either a tertiary or allyl halide, and more to the point, I know the halide is an iodide. Right? If I add ethanolic silver nitrate to an unknown, and with warming, it gives me a white precipitate, well, I know that's a secondary chloride. So this test allows me to identify not just the character of the alkyl group, but also to identify what the halogen is attached to the alkyl group. Then, at this level, at the alcohol level, we're also going to do tests on alcohols. And there are a number of tests on alcohols. So let's do what's called the Lucas test. So, by the way, this is, again, we call this ethanolic silver nitrate. So this test is called the Lucas test, and it uses zinc chloride in concentrated HCl. It's a very acidic mixture. If I have a compound that I might suspect is an alcohol, I'm going to add, because maybe I know its molecular formula and there's an O in it, right? I'm going to add to it, in a well plate, the Lucas reagent, zinc chloride in conc HCl. If I see an immediate cloudiness, that suggests it's a tertiary or allyl type alcohol. If I see slow cloudiness, often with warming, that suggests it's secondary alcohol. No reaction, either it's a primary alcohol or methanol, or not an alcohol. That should look suspiciously like what we did before for the halo alkane. That suggests that the chemistry is similar. What's happening here? The alcohol by virtue of the lone pair of electrons reacts with the acid. Let's call it HCl. Now, it could be the HCl or it could be the zinc chloride. So the HCl is the protic acid, the zinc chloride is the Lewis acid, and I can have the alcohol attack the zinc chloride as well. So the alcohol attacks the HCl, and we generate ROH plus, and we lose chloride. This species loses water and generates the carbocation. The carbocation then reacts with the chloride and generates RCl. But you're generating, you're generating RCl, which is an organic compound, in water. The haloalkane won't dissolve in water, so as it starts to form, it creates a cloudy it makes a suspension. So suspension of the organic in water looks cloudy. Now, the rate determining step in this reaction is this one, right? The rate determining step is the formation of the carbocation. So the faster the carbocation forms, the faster the cloudiness occurs, right? Because the rate determining step is the cation formation, which means the chloride attacking this is not predetermined. This happens in the blink of an eye. So we get, if cloudiness happens immediately, that's because the carbocation is stable, which means it's tertiary or allyl type. If it's a secondary carbocation, it forms kind of slowly, the same graph we had earlier, and you have to often warm it to provide the extra amount of energy. If it's not an alcohol at all, or if it's primary or methyl, can't make the carbocation, then we don't see cloudiness at all. It's very instructive that even though the tests are different, the fundamental chemistry is exactly the same. And I think it's worth pointing out that although we might view this, so here's the alcohol with the lone pair attacking the HCl, here's the haloalkane with the lone pair attacking silver. That's a base. This is really an acid-base reaction, right? It gives rise to R attached to a heteroatom with a positive charge. The RX bond breaks, the R heteroatom bond breaks, give rise to a stable product, silver halide or water, and makes the carbocation. The carbocation is then quenched by some nucleophile in the system. So the mechanism for these is exactly the same. Right? The fundamental chemistry is exactly the same, even though the reagents and the substrates are different. What else do alcohols do? Well, alcohols can react with acidified permanganate. And if we get immediate decolorization. That implies it's either methanol, a primary alcohol, or a secondary alcohol. Because you remember, we talked about for something to be oxidizable, it needs to have a carbonyl H, which methanol with 3 H's, a primary alcohol or secondary alcohol both have. So this is oxidized with manganese 7. It's oxidized with manganese 7, which is purple, into the corresponding carbonyl compound and manganese 2+. Manganese 7 is purple, and manganese 2+ is colorless. It really is a very, very pale pink, but it's functionally colorless. So if I see immediate decolorization, it implies I have an oxidizable alcohol, what's called a reducing alcohol. So methanol, primary alcohol, secondary alcohol. If I don't see that reaction, either it's not an alcohol or it's a tertiary alcohol, because tertiary alcohols are not oxidizable. They don't have this substructure, right? Methyl carbonyl, carbonyl H. And again, just to add that if you add permanganate to a compound and there is immediate decolorization, it could have also been an alkene or an alkyne, right? But I'll know the difference because an alkene or alkyne will also decolorize bromine in carbon 10 or bromine water. An alcohol will not. An alcohol will give me a positive Lucas test. Well, it might. If it's primary alcohol, it probably won't. But it could give a positive Lucas test, but it certainly won't give bromine in carbon 10. So what you're doing is you're cobbling together different observations to narrow down the identity of your compound. Magnet, right. Or I can use Jones, and the Jones reagent is dichromate. In acid. And if I see it goes immediately, it goes from orange to green, then it's either methanol, a primary alcohol, or a secondary alcohol for exactly the same reasons. Except that here, the dichromate is Cr2O7 goes to Cr3+, and this is orange, and this is green. Right? So the alcohol, the alcohol gets oxidized to the carbonyl, and the dichromate gets reduced from chromium 6, to chromium 3. Right? And that goes from orange to green. Now, as we'll see in a second, this could also mean your compound is an aldehyde, right? Because aldehydes can also be oxidized because they have a carbonyl H. So compounds having either carbonyl H's or carbonyl H's are oxidizable with permanganate under acidic conditions or dichromate under acidic conditions. One caveat here. If I use permanganate under basic conditions, and I get a immediate brownish black precipitate, right? That makes the same observation. What happens here is that the manganate goes from manganese 7 to manganese dioxide, and that's a black solid. Right? So it goes from manganese 7 to manganese 4, and that's a black solid. You should just say black, because there is a brown tint to it, but let's just say black. Continue with alcohols. Well, of course, you can pause this as you need. So I'm going to go up here to alcohols, the more reactions with the alcohols. And there's just a couple more that we do with alcohols. So alcohols also react with carboxylic acids to give esters. Alcohols also react with carboxylic acids to give esters. And that reaction is called an esterification, and we will describe that in a few seconds. Right. So what you use is CH3CO2H and a drop of conc sulfuric acid. So we use acetic acid or ethanoic acid and warm. We use acetic acid, a drop of conc sulfuric acid, and we warm it. Oh, crikey. This should be here. So we're still with alcohols. So the experiment is to use acetic acid, a drop of conc sulfuric acid, and we warm it. If we get a fruity smell, then that implies we're dealing with an alcohol. The idea is that carboxylic acids react with alcohols to generate, in the presence of sulfuric acid or dry HCl, and they generate the corresponding ester. Now, if you want to smell the ester, you want it to be volatile. You have no idea what the R group is of the alcohol. It might have 1 carbon or it might have 20. So for you to have the best chance of that ester being light enough to be volatile at room temperature, you want to make sure that the acid you use is light. Right? You want to make sure that the R of the acid you use is as light as possible. Now the lightest one is H, so use formic acid, but you don't, because formic acid is very corrosive. Right? That's part of ant venom. It's very corrosive. So the next best one, which is not as corrosive, is methyl. So we would use acetic acid. That way, you're going to ensure that the ester you make is as light as possible, therefore as volatile as possible. Therefore, you can actually smell it. And all esters have a fruity smell. We talked about that earlier, or a floral smell. So if I have a compound that I suspect to be an alcohol, I could add some acetic acid to it, put a drop of sulfuric acid, warm it. If I get a fruity smell, yep, that's an alcohol. Or a floral smell, that's an alcohol. So those are the common reactions of alcohols, the common tests for alcohols. So we go up one level. In fact, I'm just going to go ahead and erase this again. We're going to go to aldehydes and ketones. And that's where we'll stop, because the next groups we'll do, which are acids and amines, we will do those in the run of the lectures. Okay? Because so we're going to look at aldehydes and ketones. Okay? So aldehydes are RCHO, and ketones are R2CO. So the tests for these, for the carbonyl group at the aldehyde level, is first of all 2,4-DNP. Now we met 2,4-DNP before. If we add 2,4-DNP to a compound we suspect to be an aldehyde or ketone, we get a yellow to red color or precipitate. So if we treat an unknown compound with a 2,4-DNP and we get a yellow to red color or precipitate, that is indicative of the presence of a carbonyl group at the aldehyde level. So this would apply, as I said, aldehyde or ketone. So a compound, a carbonyl compound at the aldehyde level. What's the chemistry? So 2,4-DNP is 2,4, so it's 2,4 so so this is carbon 1, 2,4-dinitro, 2,4-dinitro phenylhydrazine. We've met this before. We have these in the lectures we posted on aldehydes and ketones. 2,4-DNP reacts with carbonyl compounds to give rise to a product which is the hydrazone. And if you look at the hydrazone, 2,4-DNP hydrazone. The hydrazone is exceedingly conjugated. Now, by the way, this was conjugated to begin with as well, but hydrazone has a lot of conjugation, and so the product is going to be colored. Now, 2,4-DNP also has a color to it. But if you get a yellow to red color, then, so if you get a yellow to red substance, that screams that you had a carbonyl compound. Whether the substance, so the substance can either be soluble in the matrix, in which case it dissolves and you just see a yellow to red color. That would happen if the carbonyl compound is small. So typically 6, 7 carbons in all, that would make this compound soluble. But if the carbonyl compound is heavy, easily more than 6 carbons, 6 is kind of on the fence. If it's got lots of carbons, then Van Voor's bonding takes over and the compound becomes insoluble in water, and therefore it precipitates. So you get a yellow to red precipitate. So if you get a yellow to red color, it means you have a light aldehyde or ketone. If you get a yellow to red precipitate, it means you have a heavy aldehyde or ketone. Beyond the test for the carbonyl group, there are now specific tests for substructures of this type. So for example, if I treat it with acidified permanganate or chromic acid or with Tollens reagent, so I'm just going to write it as M because this can be Tollens or Benedict's or Phelan's solution. This one, if I get immediate decolorization, so this is going from purple to colorless, manganese 7 to manganese 2, or I get immediate orange to green, that's going from chromium 6 to chromium 3, or I get immediate silver mirror if the metal was silver, or immediate dirty precipitate, which would mean the metal was copper. All of these imply that the compound is actually an aldehyde. It's not a ketone, because the aldehyde is oxidizable into the carboxylic acid, whereas whatever your species is gets reduced. So if it were manganate, it gets reduced to manganese 2+. plus. If it was chromium, if it was dichromate, that gets reduced into chromium 3 plus. If it was the metal diamino plus, that gets reduced into the metal. Right? So aldehydes are oxidizable again because they have the requisite substructure. They have a carbonyl H. Ketones are not oxidizable. So if I do a test with 2,4-DNP and I get a yellow to red color precipitate, that tells me it's an aldehyde or ketone. So I'll do one more test. I'll test it with any one of these reagents. If I get a positive result, it's actually an aldehyde. If I get a negative result, it's a ketone. Okay, I can also do another test for a different substructure, which is to add iodine in aqueous with hydroxide and warm. Ah, crikey. I should be writing this here. So if I treat this with iodine and aqueous with hydroxide and warm it, and I get, so I'm going to erase this part because you guys can rewind. If I add iodine in aqueous with hydroxide with warming, and I get an immediate yellow precipitate, then my inference is I'm dealing with a methyl carbonyl. So this will either here be H or R. It can't be like a Cl or an OH. So it's a methyl carbonyl, but it also turns out that this is true for a methyl carbonyl. So a methyl carbonyl or a methyl carbonyl would give an immediate yellow precipitate when treated with iodine in aqueous with hydroxide and warming. I'm going to go ahead and put an R here for a minute. So how does this go? Well, it turns out that iodine is an oxidizing agent. So iodine will oxidize the methyl carbonyl into the methyl carbonyl, and in the process, the iodine gets reduced into iodide ions. Right? So the iodine gets reduced to iodide, and the process oxidizes the methyl carbonyl to the methyl carbonyl. The methyl carbonyl is the active species. And the chemistry here, if you remember now, this is the iodoform reaction. The methyl carbonyl reacts with iodine in base and warming to give rise to the carboxylate and CHI3, which is a yellow insoluble solid. So this reaction does an oxidative degradation. So we break the methyl carbonyl bond, make iodoform. So this compound is called iodoform. And iodoform is a yellow water insoluble compound. So the positive reaction is the formation of iodoform, a water insoluble compound. We talked about this in the lecture at great length because it's a very useful reaction in the sense that it allows us to identify substructures in organic compounds. But it also is useful from a synthetic standpoint because we can break a carbon-carbon bond. Remember, we talked about the value of those reactions because there are not very many of them that break carbon-carbon bonds. Right, so we did carbonyls, 2,4-DNP, oxidation, including tolerance reagent, iodoform. Let's see, there's one more. I'm going to erase it in the meantime. I'll try to think of it. So there's one more that we should look at. Carbonyls. Maybe that's it. All right, so yeah, I think that's it. Okay, so that will complete the wet chemistry for